missed Monday. Did anybody make a suggestion to move that homework back yet?
No, I asked and people are like, yeah, it's fine.
Can I suggest we push back 1 week?
Yeah,
Then I have a weekend for project and a weekend for homework, and works better, but it's not the end of the world. I'm happy either way.
yeah.
So it'd be like one Wednesday.
Right, in fact, I could,
But I don't, it's okay.
Yeah, so I'm fine. Like it doesn't make any difference to me. So, just the nature of the end of the semester, things get kind of bunched up.
Yeah, I guess it would be the same day, or the Wednesday after that.
Yeah. And, it's going to be pretty far after we're done with the material. So after today, we're done with all the material. Okay. And I don't think this one should take that long. The first three are really the ones that take the longest. If you've used MATLAB before, it should be.
I think I'm actually going to have to come here to use it because I don't have a license for it.
Okay, well, you can do everything in Octave. Octave is a free alternative. Download that. Everything works fine. Yeah, and you don't need it. There's some stuff that Octave does not work well with. Some cases, but we're not doing anything that complicated. Yeah. So. Yes, let's get started. So, the homework for regression, which you'll do some cross-validation stuff that we'll talk about today. Also, it's not posted yet. Hopefully tonight. It's almost done. Sorry, we're a little bit behind on stuff. As I said in an announcement last night, I finished all the feedback intermediate reports on the projects. All of you guys are doing very cool projects, so I'm very looking forward to seeing the final reports and the posters. It's kind of a mixed bag. It takes a long time to read through them all, but I'm excited to see this stuff that you did. So I think on most, about some number of you I've talked to in person, so I didn't leave too many comments. On some, I left some fairly detailed comments if you gave enough information for me to make comments on it. And some, I didn't have as much to say because either you were doing well or I couldn't quite follow what you were saying. But in any case, if you have questions on what to do next, please come and talk to me. I'm happy to help you sort that out. That's one of the most fun parts of teaching the class. Okay, and you feel free to, before after class is a great time to do it, or office hours, or if you can't make it, feel free to contact me, find another time. Okay, and we'll talk a bit more about what goes in the final report in the coming weeks, but some deadlines are coming up soon. Okay. So today we're going to talk about There we go. So we're going to talk about noise, and let's see. So noise is is a broad topic. Probably this whole class is about dealing with noise in some aspect, and it's not clear what this actually means. And so in the kind of the section on clustering, I talked about 3 types of clustering, and this maybe covers 90% out of about, 9% of like 1 million cases, and maybe we'll do roughly the same here. Because noise comes up and affects data in many different ways. So what I'm going to try and do today is to first kind of give general classes of noise, a good way to think about the different ways that you can have noise in your data, and then talk about some broad ways of handling the noise. So let me start by talk about some types of noise. So the first type, so these are, so I'll call these, so these are spurious readings. And so often when you think of these, you think of things like, outliers, and so we'll talk about identifying and removing outliers in the lecture today. These are sorts of noise where you're, like you have a typo, you put the decimal place in the wrong spot. This happens, right? These are things where if you were to plot the data, you'd probably quickly recognize this data point is way different than all the others, right? So if we're doing some clustering of data, and and we looked at a data set like this, and then there's one data point out here, it may actually be even further out there, and trying to draw it on a single screen with the right resolution wouldn't do it justice, right? These are often things which are really far away. And so if we have some, and so they don't really fit the rest of the data, and you don't want these to affect your algorithm. So, the old school approach of doing this is, okay, kind of look at your data, plot it, and then these things will kind of jump out, and you can kind of just throw these things away. And when you're collecting data, if you're a scientist, maybe write in your lab notebook that you did this, but then you kind of move on and pretend like it was never there. And you can still do that to some extent, and we'll talk about how to automate this process a bit later. But when your data set is collected completely automatically, sometimes it's hard to know whether it's an outlier or it's not, right? If it's 2 dimensions, you can draw a picture, you can see. If it's 1,000 dimensions, it may not be so clear, right? Okay, the second type is some measure error, okay? And so this is more like things that are not so spurious, but that are kind of, there should be some value you expect to get exactly, and you don't quite get that exactly, right? So, so I would say these are like small, so full dimensional noise. So if you look at like this clustering example again, in this case you have some model that is the center of the clusters, and then all the clusters kind of fall inside of these ranges roughly here. But kind of by saying that if this was like k-means clustering, you identified these centers, you're saying, well, the true value is really the center here. This is what's really we want to identify. And maybe these other data points that are not quite at the center, that's because we measured them wrong. If you're trying to keep track of your weight every day, and you go on the scale, and some days it's a little bit heavier, some days it's a little bit lighter, you get a little bit of error in this process. Now scales are much more accurate than they used to be. It used to be you go to the doctor and you got this slide thing, and who knows what's going on, right? But you can still get this sort of small measurement error in the process. So if you're doing like readings of like some sonar or something, it's not going to be completely accurate. And sometimes you choose not to make it accurate just to make it more efficient, or because you don't think you need the accuracy, right? Another example is like if you're doing some PCA or you're doing like some linear regression, your data is here, the model is the red line, and it's not exactly in the red line, right? So this is because you're not exactly hitting this model. Maybe this is because you measure there, maybe it's because there's some other variability that's some outside factors. So that's, they aren't exactly from the measurement, they're because there's small variability that isn't the main structure of what's going on. Right? That's the same class of error as I'm talking about here. Okay. And then the third type is, so roughly call this the background data. And this would be where there's some model and then there's some noise and there's some crazy things, but there's some, occasionally, there's a few other points, right? These may not be quite these spurious readings which are way off to infinity, which you really need to deal with, but they're kind of filling in the background. You may have 1,000,000 points and then you have a few hundred which are just kind of out here someplace. They don't really fit any of the models. Is this point in this cluster or this cluster? Maybe it's in the middle. It doesn't really fit to one of the models, even with a little bit of noise. But it's also not so much pulling the model off. It's not causing you to put another center way off at infinity. There's kind of just annoying. These techniques you can kind of, you'd like to just, your model should be fairly, it's easy for it to be robust to these sorts of noise as well. This could also include things like where if you're doing, so if you're doing like a recommendation system, you have like a bunch of people and they've watched movies and then they rate certain movies, and then there are tons of movies that that these people don't rate at all, right? Most movies across most people are not rated. It's very sparse. So you have lots of missing data. So what you typically do is you kind of assume that these values are going to be something like the average of all the movies that this other person has rated, or the average of what everyone has rated all the movies, and just pretend it's that, and then you can kind of go on with your with the rest of your model. Now, this maybe on aggregate is true, but on average may, like, on an average and aggregate it might be true, but in some cases it's definitely not true. Someone could go watch the movie and say, oh, this is great or this is horrible, when you had said, oh, you thought it was mediocre otherwise, right? So it's not giving you the right value what it should be giving you, but it's there in the background. Okay, so often people find ways to kind of make these not matter, but maybe if you knew the right value, they should matter in some way. So you kind of try and make these kind of, most models can just kind of, hopefully these aren't really influencing what's going on. Okay, so these are kind of the classes. I think most types of noise fits into one of these categories, and how you would deal with it is going to kind of fit within one of these cases. If your algorithm cannot deal with this sort of data, it's probably not very stable at all. K-means clustering, for instance, may have trouble with this one if there's too much of it. So the measurement error is kind of built into your model is trying to say these are often, you're trying to minimize often this measurement error. It's usually what they're built around. They're usually built around thinking about this type of noise. And then the outliers are things like we talked about, this things like the L1, like the regularized regression. Those are meant to deal with the spurious readings, right? So these are kind of the main classes of approaches. Okay. So now what the rest of the lecture I'm planning to do is to, try and talk about several kind of specific approaches, not necessarily to dealing with these specific types, but some kind of themes important aspects that come up that I haven't really touched on yet. So the first one we'll be talking about so cross-validation. And many of you may hopefully know, or maybe know something about cross-validation. We'll also talk about how this relates to understanding the generalization error and finding parameters and bootstrapping and some other aspects as well. Kind of fit these all together. The second thing we'll talk about is these outliers specifically. Kind of what are the standard ways to do this, and what should you really be watching out for? Okay, and then the things we may get to if there's time. So one aspect is looking at this data that's uncertain. So sometimes you're given data, but instead of just giving a bunch of points and say, okay, here's the data, you know, go and deal with it, you say, I actually know what I don't know about this point. Instead of it, it's not in, it's a known unknown or something. I have some, say, I know this point, this is kind of where my maybe most likely location, but there's some probably distribution describing it. And so I can have more information about the individual noise of each of the points, or each the points on average. And so how do you incorporate this into this modeling? And then we may talk about some robust, so some of these robust estimators. I talked a little bit about them in the introductory lecture on regression as well. But how do you think about things that are provably stable to various sorts of outliers and noise in a different way than if you do the regularization? Okay, so this is the plan for this lecture. Okay. Okay, so let's talk about so cross-validation. So the first point to come across here is that I believe basically any data mining algorithm, so if there's an algorithm that let me try and write more carefully here, that that actually deals with the noise, then there's this hidden problem of how much noise. So I'm going to say that this is going to have a parameter. Okay, so it has some parameter that tells you how to deal with the noise. This is almost, I'd say this is that this is basically required. Okay, so examples in clustering. So this is the value k. Okay, so how many different clusters do you have? If you thought there was no noise in the data, then you could essentially say every distinct point is its own cluster, right? Because there's no noise. Each of them is different, right? Each is its own, each is its own beautiful snowflake. How could I ever, kind of say these are similar to each other, right? So you want to say there are only k clusters, right? So if you're doing if you're doing PCA, then it's going to be the so the number of the principal components you use, right? You're saying that you have this very high-dimensional data, and there's some low-dimensional subspace which describes this data that's going on, and everything coming out of that subspace the other way, this essentially is noise. It kind of is not really telling what the data is really about, right? So it's a number of principal components tells you what part is noise, which part is not noise. So if you're doing regression, then it could be the degree of the polynomial So, so one thing we didn't really talk about much in class is that you can take these linear regression problems and kind of take all pairs of variables that you have and look at these becomes, and treat each of these as a variable, then this becomes a polynomial regression of degree 2. You can look at all triples of variables. Each time you do this becomes a more expressive equation, more expressive model, and the degree of the polynomial that you're willing to consider tells you how much you're trying to fit this data, right? So the other thing would be the regularization parameter. Right, so we talked about the lasso and the ridge regression. It'll be simpler to talk about the ridge regression. So I'll kind of write down this model here. So we'll have some loss function on your data and some parameter alpha, right, where this is kind of the y value of your data minus the x value, which may be multiple dimensions, times your model. So let me write this differently here. So it'll be a function defined on the data, and you takes in a model and this parameter alpha. Okay, and so you look at this model. So this is a linear equation, this linear model. Usually look at the 2 norm here plus alpha. Right, so now this could be, this px and py are the dimension you're predicting with a bunch of other dimensions, and you have n data points, and then this is, if you have d dimensions you're using, this is a d-dimensional vector, right? And so then this is the 2 norm, so the sum of all the squared elements, the square root of that, right? That's the 2 norm of this model vector, and you penalize it for being large. So you want to minimize this total error function. It's not only a function of the model, but also this, how much you penalize the model for allowing, for having large components in it. Right, and so now clearly this is a parameter. The larger you make this, the less noise you can have. The model has to be essentially smaller and simpler. If you make this very, very small, if you make this 0, then this is irrelevant and you just get this least squares model. Right? So this sort of parameter comes up, each of these things has some parameter like this. Right? As we'll see in Outliers, this is going to come up as well. And so, we talked a couple times about how do you choose this parameter. And so typically what you have is you have some way of measuring the error, and then you have some parameter. And if you set the parameter in some value, and sometimes it's large, sometimes it's small, but in the case of k, for instance, for k-means clustering, then what happens is, as the parameter k is small, you're going to have a lot of error, and then as the parameter k gets large, your error is going to go down. Like if you have n points, n cluster centers of n data points, your error is going to be 0, right? And at some point, it kind of starts leveling out, and this is like the elbow. Right, and so you can plot this and then look at this parameter here. If there's one parameter, you've reduced it to one parameter, then often you can say, okay, let's try and find this spot. Okay, and this seems kind of ad hoc, right? This is not very, very satisfying. So in some cases, what you can do is what's this? It is this technique cross-validation, which is kind of going to be similar in spirit to this, but it's going to be more formal. Okay, and to introduce this, you want to think of your data. this is my data. Okay, and the model is that each of, so this is my data P, this is PI. You'll say something like the model is that PI comes from some distribution, and there's some parameter theta which describes this distribution, and each data point is coming IID from this distribution, right? So talked about IID means each is identical, they all come from the same distribution, each is independent of the other ones, right? So it's independent and identically distributed. So that means that each row, each data point is an independent observation. And so if you think of it in this model, the goal is to think of, well, this is the data that I want to use to find some structure or to learn something. And I don't necessarily just want to learn something about this data. I know this data. I want to understand something about other data that I would also get. If I kept getting more data, then I want to know what's going to happen here. Right? Any data point I have, I can look up and see what the value is. I kind of want to understand some general properties of what's going on. Right? So this is very much a perspective I hope is taught in the machine learning class. And basically, instead of understanding just what you have some model, and then so so this is a model, and then you have some way of measuring the error on your data and the model. An example of this error might be so one example might be your data is P, and then it was this loss function on the model, which was A in the example before, and maybe you measure it with this alpha parameter. Maybe this is the loss function, or maybe it's LP M0, right? So you say, when I measure the error, I don't really care about that penalizing that extra term. I just want to measure the raw error, the actual least squares error, right? So I have some error function on the data, and I don't just want to understand the data I have, because I know that data. I want to understand what it's going to be, and if I got future data from the same distribution. Now, the problem is I don't know what this data is because I don't have it. So how will I know how well it's going to do? Well, the idea is to take your data and to split this data up into two parts. And you have a training part, and you have a testing part. Okay? And so you're going to build your model on the training part, and then you're going to see how well it does on the testing part. And if these are all, and this kind of assumption that it's IID, that it's all the data is coming independently, makes this okay. Because you're saying, okay, I have some data that I'm using as my view to train on, and that this test data is going to look like new independent observations. The same way if I got new data coming here. And so it's understanding what looks like a new data means that it generalizes to new data, and so this is thinking of often what's called the generalization error, is the error you would expect to get on new data you got. And this is what you should be thinking about measuring, not the data, not the model, not the error on the data you have, on the data you would get next. And so this is trying to simulate this by, so kind of build the model. So build the model using P train and say alpha, and then so then evaluate the model as the error on P test and the model. Okay, so build it on the training set and then evaluate it, the error, how well it does on the testing set. Okay, and so if it does well on the error in the testing set, then you kind of, this tells you how well it should be doing on new data that you don't have yet. Okay, So this is kind of the general idea, but now I said, I'm coming back to this parameter. I said, I want to learn with respect to some parameter here. So I kind of want to do this same process, but in order to figure out what is the best choice of this parameter here. I want to find the parameter, so I'm going to do best on new data. So I still may want to keep some data around to evaluate how well I'm doing. Let's actually just formalize this. Let's take this data at the bottom to evaluate. At some point, I want to say, okay, how well did I do? But I want to use the testing data to learn this parameter instead. Right? So this actually goes here. And then instead of evaluating, we want to put another step in the middle here. Learn alpha. So I want to say alpha is going to be equal to arg min of my choice of alpha of LP of the model as a function of alpha. Okay? The model I found using some alpha on the P test data. Okay, so I want to take this data here and I learn alpha on it, and the training data will allow me to build these models for various alphas. Okay. So let's go through a little example of this, like in more, not specifically work out the numbers, but just to kind of walk through this a bit more. Okay, so this evaluation, it's a little confusing because you usually talk about cross-validation as doing one of these two things, either evaluating or learning this parameter. But you may want to actually do both. You can't use the same data to do both things, and so that's why it's got a little confusing here. So let's just look at an example where we have data where I'm breaking it, we'll call this P, and this is P train, and this is P test, and then I will pretend I've got more data down here that I can get later to evaluate it, but I won't worry about the evaluating now. I just want to learn the best model here, okay? So how you would write this, let me write this out mathematically and then we'll try and, so I can define, let's write M, let's write it as this, so let's look at this problem of where this data P, I can break into Px and Py, and my goal is to find the so my goal is to find the best linear regression that minimizes the least squares error, but to minimize it on new data, on data I'm going to get. So the generalization error is small, and I'll do this using ridge regression. So I'll use so I'll use ridge regression. So what I want to do is to so I want to define model, and so again this goal is Py minus Px times some values A, right? So I want to minimize, I want to find the coordinates, or this vector A, these coefficients, right, that minimize this loss, right? So this is L of P of A, and then I'll use this alpha parameter plus alpha And I'll just use 2 because now I have a closed form for solving this for any given value alpha. Okay? And so I want to, first thing is to, one is to find find alpha such that P, so I can solve, yeah, so before I do this, if I set this up, there exists this solution, we'll call this A alpha hat, which is going to be Px transpose Px plus alpha squared, the identity inverse Px Py. Right? So given this loss function for a fixed alpha, then if I do this, it's going to give me these optimal coordinates for this function of alpha. Right? So I can, for any data set in alpha, I can solve for the best A. And so now, what my goal is to find alpha which so minimizes the loss function on P train, so on P test. So I'm going to evaluate it on the test part of the data for a model alpha that's learned on the training part. And with my loss function here, I don't need this regularization parameter. I just want the least squares fit. Okay? So what does this look like? I've built a model on the training data that depends on alpha, and then I evaluate it on the test data. So I need to now, I have some function that is, so this is now a function of alpha. This alpha comes up here, this is the parameter. So I have an error, so I can calculate, I can put this whole expression here inside of this loss function, right? So I have this loss of P test of this expression here is going to equal, because the 0 here is going to be Py on the test data minus Px on the test data times A alpha hat. And this expression goes into here. Okay, so this has this alpha term, and so everything else is fixed. Everything else is given to me. The P test, these two parts are given to me. The P, and these are the train parts. This is the train, and so these are all the training data, and I just have to find this alpha which minimizes here. Okay, so now it's kind of complicated. You know, you could probably you can kind of do like a, I don't know if you can do a gradient descent on this, but you can test a bunch of values alpha at the least and find the one that minimizes and kind of do like a binary search on this. This should work well in most cases. If you're doing if you remember, if you're doing the lasso, when you solve this, you solve for all values of alpha in this case, or all values of S. So then you can go back and evaluate all values of S on the test data. Okay? All right, so this is kind of, this way you can use cross-validation to pick out which value of alpha or which parameter is doing the best, based on some loss function by dividing your data into the training part and the testing part. Okay, is this clear? Okay, so what was kind of lacking in this procedure? What seemed that, so there's something that seemed kind of arbitrary about this, right? I split, so standard cross-validation, you take your data and you split it into the training and the testing, and you're effectively using, you're using all the data to either do the training or the testing, but this split seemed kind of arbitrary. What if I split the data differently? What if I trained on this part and I tested on this part? Why did I split it this way? Would have gotten more information if I'd done a different combination of how to split this data. Right, so one option, there are a couple of variants of this. One is k-fold cross-validation. And then the idea is that your data is split into these k pieces, 1, 2, 3, up to k. And so you train on all sets of k-1 parts, right? So I could train on these first parts, and then I test on the other. And then so then I test on this last part, but I could also train on the first k-2 and the kth one, and then test on this one, and so forth. Right? So this way I get more views of the data from training and testing. I don't just have one split of the data, now I have k different splits. Okay, and so then I want the error that minimizes, I want the alpha parameter or whatever that minimizes the sum of all the errors across all these different ways of splitting. And so then in the limit of this is called the leave one out cross-validation. And there the idea is that you always leave out the ith one, and so this is the test in the ith phase. This is the only test point, and you train on everything else. So this has the advantage that now my training set, before, like over here, I'm training on maybe this is 1/3 of the data and this is 2/3. So I'm only training, I feel like, on 2/3 of the data. I'm kind of not using this to do my training. It feels like I'm throwing it away. Here I'm training on all except one data point, and then I test on this one, and I still get to test on each data point based on training on all the other ones. This takes, if you have n data points, you have to train n times though, so this takes longer. Whereas this one takes k times as long, and this one just does it once, right? So you get this trade-off where this is more efficient this way, and this gives you more information. You can do even more, there's even more complicated things that people typically don't do. You could say, leave every 2 out, right? Then you're going to get and choose 2 different training sets. But they're going to be they're already very similar to each other. So it kind of, it's usually something along this spectrum is what people use. So what would happen if, let's go back and make a point. What would happen if you tested, what if I did this procedure, the same procedure I described here, but I didn't separate the training and the test set. I did both my alpha, my A hat alpha, I used on the full data set, and I also evaluated on the full data set. Well, what would happen then? Yeah?
Try to overfit the data, and you kind of create a model that allows all the
Yeah, and so so in particular with respect to this parameter, what does that? Yeah, that's right. You would overfit the data. With respect to this parameter, what value of alpha am I going to find? it'll always be alpha equals to 0. I want to minimize this loss function with alpha equals to 0. Right? And so the model that fits this best is exactly going to be this. This was the closed form solution for that. Right? So if I'm finding something that's not, if I'm finding something different, that means that 0 was not, it's not the right model for generalizing, right? And the issue is that you're going to overfit to the data. In the case with regression, it's kind of harder. Just a linear regression with regularization, it's harder to believe that, am I really overfitting or not, right? If you're doing like this polynomial regression, you can make these like spline curves that actually go through every single data point if you make the degree high enough. And so you get a new data point, it's not going to lie in this very complicated line. It's kind of easier to see there. In this case, the overfitting is going to correspond with an alpha equals to 0, and you're going to see that. Right? So you want to kind of separate the training and the test data. Otherwise, you're not going to learn. You're going to learn the most complex model possible. Okay, so the next thing I want to mention is that if you keep going on this spectrum, what you're trying to do is to build a model on the full data set here, right? If I did it on the full data set, I'm going to overfit. If I do this one, I'm taking too long, and I'm still not quite getting to the full data set. If you only have a small amount of data, say you only have 10 data points, right? Maybe leaving out 10% of your data still feels like a loss, right? So some of the faculty here work with like building some model on some like these MRIs of human brains. And these are expensive to get, but they're also hard to get in use in research because you have to get the patients to sign all sorts of waivers. And anyway, so that they'll get like 10 data points. And so they don't want to waste any of them in building the model or in understanding how well this model fits. So you can't avoid this with the cross-validation, but if you go back to the other form of this, where you're not trying to find these parameters, but you're trying to evaluate how well you're doing, right? So if you go to a medical doctor and said, yeah, thanks for the 10 brains, I built this really good model using only 9 of them, right? They're gonna be like, well, why didn't you use the last brain? You want to use all of the data that you can. So you somehow use this. So if you go back to this picture, if I wanted to say how well I did, I'm going to train on some, test on some, I need to leave some left to evaluate how well I did. If I want to kind of scientifically say whether this was good or not, statistically in some way, I needed to leave some data out. So there's one way kind of around this that is, where are we here? So this is called, bootstrapping. And so that's to take your data, let's say it has n data points, and you're going to generate a bunch of new, so a bunch of these new data sets. I didn't draw that very well. Okay, this is, so new data sets. Kind of like this. Right, so these new data sets, I'm going to generate k new data sets, and so each are going to be of size n. Okay, so I want to understand how well a model I built on these n data sets can actually be, without wasting some of the data to do the evaluation. Okay, so I'm going to generate these k, for some value k, new data sets that are each of size n. So how do I do that? What you're going to do is to sample, so with replacement. Okay? So each new data set, so if I go from P to P1, P2, P3, up to PK, right? So each of these data sets, so PI is going to get N items from P, and these are going to be IID. So if I sample with replacement, if I want to sample without replacement, right? If I was essentially this trained test model here is saying, I'm going to sample some to be in the test set. I'm going to pull some randomly out. Maybe it's 10% randomly out. Because they're IID, I can just take the last 10 and it doesn't matter so much. But I know I'm not going to pick ones twice. I'm going to pick out 10 distinct ones, 10% of distinct ones. This says pick them with replacement, and so that's independently. If they're going to be independent of each other, then I might pick the same one twice. Okay, so if I pick these IID, it's with replacement, and now I can do this until I have a data set of size n. Some of them are going to occur twice, and on average, you're going to get about 66% of them are going to be distinct, as it turns out, in the set. So each data set is going to have about 2/3 of them are going to be distinct, and the other ones are going to be copies, sometimes multiple copies of some of the existing ones, but they're each going to be of size n. And because I drew IID from a data set that was supposedly IID from another model, it kind of is simulating like these are each IID data sets. And so what you do is you build model MI on you have some algorithm on PI, and you do this for each data set, and you're going to get a collection of these models, MK. And so then you can evaluate, you can kind of, say, draw another IID data set or something and evaluate the error or the variation in these models and understand the error. Okay, and so this is kind of a different way of understanding the error, and it's related to this cross-validation, but it's kind of an extension in a different direction. Okay, so that's kind of, I just want to put all these various things in context. There's some similar things called like the jackknife and so forth that the differences are kind of subtle, but these are kind of the main approaches to evaluating your generalization error and learning these parameters. Okay, so that's what I want to say about cross-validation and related topics. I want to talk about outliers now. Sound good? Yeah.
Can you tell me one more time how is this different from the cross-validation?
Yeah, so this is used, so there are two things cross-validation is used for. Right? If I go back to here, there are two things. One is learning the parameters, and one is evaluating how well you expect it to do when you get new data. Okay? This is used for evaluating how well you expect it to do. You could leave some data off to do that and just keep this separate data. I can't use the same data I use for testing because my model that depended on alpha actually used that data. So it's kind of cheating to use this data for evaluation. So I need to leave some data off. So let's say I didn't want to waste any of my data points to do that. So then instead of dividing up your data, you kind of sample with replacement and build a bunch of these models independently and then see how much variation there is in these models. If there's a lot of variation, then you probably have a lot of noise. If there's not a lot of variation, you don't have a lot of noise. And there's some details in how you go about kind of mapping this to some actual error model and so forth. But that's the general idea. That's good. Okay, cool. Okay, so outliers. Yeah, so say outliers are kind of the cause of and the solution to all of the problems to all the problems in data mining. If there weren't any outliers, a lot of these problems would be easy. And if you could identify the outliers and get rid of them, then the problems would become easy again. So if you can deal with outliers effectively, then you're going to be doing well. The problem is that outliers are kind of this ill-defined notion. There's kind of defining an outlier is similar to the modeling you come in defining what your generative model of the data is. So the outliers are usually very tied into this model, and that's not always the case. But in most interesting ways of defining them, that's so that's what's going on. So if you already have the model, then you don't need these outliers. Okay, so we'll talk about two main approaches to dealing with outliers. So one is the so the general approach people think of is they're going to find the outliers and remove them from the data set, and then rebuild your model on everything that's not the outliers. And we'll talk about kind of the themes that come up here, and then the general challenges. And there's kind of some other approaches that get around some of these challenges. So there's these density-based approaches, where you kind of say an outliers are data points that don't have a lot of other data points near it. Right? That seems to be the definition of an outlier. And sometimes that makes sense, sometimes it doesn't. And if it does, then these can be very useful techniques. Okay, so to find and remove outliers, there's kind of a very standard approach to doing this. And this should be kind of the first thing you probably will think of. You're going to have 3 steps. You're going to build a model M from input P. 2, for all points P in P, so you're going to calculate the residual of P, which is going to be something like, usually is some distance from the model of the point on P, the point in the model that best represents P to P. Right? So if this was k-means clustering, right, then the model is the center, and the distance from the point to the center is the distance to the closest center. Right? So this is the residual. In regression, it's the M of P is the point on the line, right? So if I have a bunch of data, and I have some best fit line through here, and I have some data point P, then this is M of P, where this is my model, right? So the line is the model, P is the data point, M of P is the mapping of the data onto the model, and then this curve here, this is R of P. So this distance from the point onto the model. So this is the residual. Okay, and all right, and so now, and then you want to say if RP is too large, it's an outlier. You know, and then you throw this away, right? So if you built a model, a point has a very large residual, then you want to say this is an outlier, right? So this is kind of like, now hopefully this makes a lot of sense. This is very clear. if I explained this on the first day of class, probably this wouldn't have had as much context, right? We talked a lot of time about defining various distances to models. We talked about building models from regression to these streaming things, to clustering, you know, and so this should have some context now, right? Should be an obvious thing. You want to build some model of your data. You want to calculate some distance to the model. We talked with some group who's doing hierarchical clustering, and how does this fit within hierarchical clustering, right? You can define a distance onto that cluster in a natural way within that setting. And so this residual still makes sense, even if you don't have like a center in the same way. Right? So then you can define these residuals, and then you have to find them. If they're too large, you want to throw these away. Okay, so this seems like the obvious way to do this, but how do we define this too large here again? Right? This is again some parameter that we have to do here. And so you could learn this parameter using some cross-validation, right? Where you had the model that you built on the training data, and then you evaluate it on all the test data points so that it's as small. But you have some, you may need, this model itself may have needed another parameter in addition to dealing with outliers. So you would need to first set aside some testing data to learn the parameter, and then you have another parameter to deal with what outliers to throw away. What seems kind of wasteful about this approach? Like, what's the point of throwing away these outliers if we've already built this good model? Right? If we have this nice model here, and we built it and we trust it to filter out the outliers, then we already have the good model. So why should we throw away the outliers then? We want to work with this model now to understand the data. Right? So this technique is built on the premise that you can build a good model on the full data set in spite of the outliers. Right, so this seems like the obvious things to do, but it's kind of built on the fact that outliers shouldn't affect you anyways because you had some robust way of building this model. So it's kind of like so it's kind of like it's like this chicken and the egg problem, right? If I knew what the outliers were, or if they weren't affecting my model, well then I don't need to filter them out. If they are affecting my model, then how can I build a good model and throw away the outliers, right? If this was k-means clustering and there was one point off by itself, and so I built a clustering and that point was one of the centers, then that one has a residual that's really small. I'm not going to throw it away. Right? So you kind of, there's some kind of inherent strangeness in what's going on here. And I mention this because this is what most people think of in doing in finding outliers. But there's kind of this issue of if you have the model already, then why do you need to throw away the outliers? And if the outliers are really affecting your model, then how can you trust the model? Okay, so still there's some issues where you can beat this a small amount. You can try and so put some iteration on top of this. So instead of doing this, you have another step that's throw away that outliers away and call this p hat, and then go back to the first step and build the model over again. Hopefully now the model is better, and you can filter out more of the outliers, or maybe you kind of say, they're all close, I don't need to throw any more away. But now your model is maybe a little bit better. So kind of thinking of like when you ran the Gonzalez algorithm for clustering, this was a good starting point, the k-means plus algorithm. And then you ran Lloyd's on top of that. That's going to kind of give you a little bit more refined solution, going to make sure the centers are on the cluster, the center of the centers are in the center of the data to represent instead of some point in the set. So it's going to kind of refine this process by kind of iterating on top of here. If you iterate, though, there are a couple things you also need to be worried about. What if this too large? What if I took this too large and this was, say, I didn't know what the distance meant, so I said, this was, say, 5%. So it's the largest 5%. Right, so I took the largest 5% of the data points and I just threw these away. I said, I don't know what the right distance threshold is, so let's take 5% and throw them out. What would happen if I iterated this algorithm?
You run out of data.
Yeah, you're going to keep throwing away data every time, right, until you don't have any, data left, right? I mean, at 5%, it's going to kind of slow down how much data it throws away every time. Maybe at some point you have less than 20 points, so you're like, okay, I don't have a 5th percentile left. The same thing as if you threw away, say, so 50 data points or something like that. So eventually you would definitely run out. So this would, so this could run out of data. And so if you, so it's probably better to instead, to pick some threshold on this on RP. So some distance threshold. So I have some knowledge about what you think is an outlier. And the advantage of this is if you pick some distance threshold, either just without iterating or with iterating, it kind of gives the data a sense of scale. So some problems, depend on how you look at them. Like if you look at patterns in the weather, there's a daily scale and there's a yearly scale of weather patterns. So there's often an inherent sense of scale, and you can choose which one you look at. And so this allows you to sometimes give some sense of scale in the problem. And this makes sense to be a user-defined threshold. That's a modeling choice that you make before you start the problem. Right? And then if you do that, it can be fairly reasonable. As another kind of weird aspect of this, like what percent do you throw away? Well, let me just pose another it's like another thought experiment here. So let's say you had data from a normal distribution. So this is another name for a certain standardization of a Gaussian distribution. This is these bell curves, right? And so it looks like this, where you have some mean value that you expect your data to be, and then it's usually here, and this is the probability distribution. So you get something where something, say, like within what's one standard deviation. So it's often called sigma. Then you have this is 66% of the data is in one standard deviation. If you go out to 2, so this is another sigma out here, then you get something like 95% of the data. If you go out to 3 standard deviations, my drawing ends up being pretty reasonable here. This gets to, this is another sigma, and you get to 99% of the data basically. And this kind of keeps going. And a lot of data follows this pattern. If you've heard of the central limit theorem, if you make repeated observations and enough in a certain way, eventually your data kind of starts looking like this normal distribution. So this sort of thing comes up a very reasonable model in a lot of cases. Okay, and so, but it doesn't stop. I can go out 1, 2, 3, 4, 5, 6 standard deviations. At what point do I say that this is an outlier? And at what point do I say, well, it's in this normal distribution? This is defined. I'm not going to scale it exactly right, but it's basically, it's the e to the power mu minus squared, right? So this is essentially the normal distribution for a value x, the probability at some value x. So if this is the x, the distance from mu squared and e to the minus that. So it decreases exponentially, but even if you're very far away, this is still non-zero. And if you do this enough, there's going to be some data points out here. At what point do you throw them away? Or do you really need to throw them away? If you can fit a Gaussian distribution to it, or normal distribution to it, then that's good enough, right? So why would you throw away these outliers? Your goal is to build the model. So, okay, so just kind of, this whole thing of throwing away outliers is a tricky process. Okay, so I want to give this different perspective, the density-based approach. And so there's some settings where this makes sense, where the idea is to kind of, so you have some points at P, and let's say it looks kind of like this, and you kind of build some density function on top here. So one way of doing that is for any data point, say draw a ball of a certain radius and count so the number of points inside of this ball is the density at this point. This is kind of a very rough way of doing this, but this works up to some approximation reasonably well. You can instead put like a Gaussian kernel on top. That's going to work better. That's kind of what's called a kernel density estimate. But just draw a ball of a fixed radius, count how many points are in there, and if this number is below a threshold, then the point's an outlier, right? So I have one data point over here. I draw the same radius. This has 0 points in here, where this one has, say, 5. Right? So 5 is above the threshold. If the threshold is 2, then I throw the point away. I say the point's an outlier. Right? So this works fairly well. I need this parameter r. A different way of doing it is to do something like pick a point and find the kth nearest neighbor. Right? So 1, 2, 3. So this is the third. So this is the third nearest neighbor, and then the density has to do with this radius. So the larger the density, the smaller the radius. So then the density based on k is going to be something like 1 over r. So then if this radius is large enough, then you would throw away a point, right? To get to the kth nearest neighbor from this point, I may need to go out to here. So this radius here is very large, and I would throw this point away. And so if you can think of your data in this way, then this works reasonably well. I guess if you have very high dimensional data, this is going to behave more strangely, though, typically. Distances tend to look very similar in high dimensions for a lot of data points. They all look to be about the same distance because things kind of average out in a lot of cases. Now, if your data is inherently lower dimensional, then this sort of approach can still work, but there's kind of a lot of issues that arise that are kind of unintuitive in high dimensions in these approaches. But this works in some cases, yeah.
If all the points tend to be about the same distance in high dimensions, then
Yeah.
do outliers even exist in high dimensions?
Oh, well, so it could be. I mean, the same distance, you have to have some setup to get there, right? There could be a case, let me try and draw a picture here. So you have some points here where these points are in a plane, and then there's some other axis, and all of these points lie in the plane, and you have one data point which is up here, which goes up in these planes, but all the other ones project onto you know, they all lie in this plane here. Right, so I have one data point off the plane, but I could structure them such that they're all roughly the same distance. This other, now this might be like a 10-dimensional subspace, and this is one other dimension, and this one other dimension does not add too much to the distance that lies within the subspace, because this one was fairly centrally located. But it's the only one that didn't lie inside of this small subspace, so it's still an outlier. So distances alone might not work. Right? You may want to, again, if you can find this model here, then it's the distance from the model is going to be very small for all these points, but very large for this one, and then you can identify it. Right? So they all look about the same. Is true for things like if you generate them from a Gaussian distribution, that'll be about the same if you put them inside of a high-dimensional unit box or unit ball. These sorts of phenomena are going to exist. If there's structure to them, it may not exist, but it still might in some cases like this. So there's some weird stuff that can happen. And so I wouldn't trust a lot to do with density in high dimensions. Density in high dimensions get very strange and hard to think about. You're essentially trying to fill out a high-dimensional space that kind of complexity grows exponentially with the dimension with the fixed number of points, and it's hard to have those grow exponentially to really believe that you can fill out all those dimensions with the density. So I don't know if that makes sense to you, but that's kind of how I think about it. So okay, so I mentioned one variant of this density-based approach, which is cool, and this is called the reverse nearest neighbor. And so the idea is you have a bunch of points, and so for every point you find its nearest neighbor. Right, so every point finds its nearest neighbor, but then what you want to do is go backwards. So say from this point's nearest neighbor is here. So let's say this guy, let's label these. This is P, this is Q, and this is R. So so let's write this in some notation we used before. From the distance from P to its nearest neighbor in a full, let's call it point set X. For a point set X is P, let's call this Q. And so if this is about the same as the distance from Q to its nearest neighbor, and we'll call this R, right? So if I look at the distance from P to its nearest neighbor, that's P to Q here, and the distance from Q to its nearest neighbor is about the same, in this case R, even though it's not the same point, these distances are pretty similar. That means that these are probably close, whereas if I did the same thing from this data point over here, the distance its nearest neighbor, say this is P prime and Q prime, and this is R prime. So Q and R prime are very close to each other. P prime and Q prime are very far. So this would be much bigger than this. That says they're probably not, that it's probably not. And so then you can just look at like the ratio of these two things. And this kind of makes sense. A factor 2 or 3, it doesn't have units. You don't have to worry about what distance you used to kind of think of a very easy to understand threshold. The problem, of course, is that you could have 2 points that are off by themselves, and then like a million points over here. These points are their own nearest neighbors, so then this doesn't work anymore. So you could replace this by, say, the kth nearest neighbor instead of the first nearest neighbor. And that's more robust, but you again have to choose a value k wisely. So if you choose the first nearest neighbor, it doesn't work, but the second nearest neighbor already works. So if you said like the 10th nearest neighbor, this is going to be more robust. So take the distance to the 10th nearest neighbor, and so if the distance from this guy to its 10th nearest neighbor is too different, then, or even to this guy's nearest neighbor, then if the distance to the kth nearest neighbor is less than this guy's distance to its nearest neighbor, then that's or the one way or the other. You can kind of play various ways with that, and that's going to make this process just more robust. But again, you have this extra parameter. Okay, I just want to say one more thing quickly. I wish I had a couple more minutes. So one challenge that comes up is these heavy tail distributions. So I talked about this normal distribution before. This had the property that it trailed off exponentially. So you could get these things like 3 or 4 standard deviations away, but they're very, very unlikely. They're cases with low probability. There are these other distributions like the zip distribution, which was what the zip look like. It's the probability of the ith thing in the zip distribution is going to be roughly some constant times 1 over I. So it's not decreasing. So this is the ith furthest thing away, or the ith item in a sequence. The probability of it is not decreasing exponentially. That would be like 2 to the minus I. Instead, it's decreasing polynomially. And maybe you take this to some constant power. Okay, so this sort of distribution, you can't, depending on what the constant is, you can't often, if you raise the certain powers, you can't even integrate this if it was continuous, you couldn't even, it doesn't have an integral. So it's going to be something where the normal distribution might look like this, actually, it's maybe a little extreme, right? Kind of like this, where the zip distribution, or this zip is discrete, there are continuous versions which kind of look like this, and they never quite feels like it's going to 0. And so it could be something where something that looks like the tail, this is like 30% of the data. Okay, and so a lot of what happened in the dot-com boom was internet companies figuring out that this tail was untapped. There were a lot of companies that tried to do this, and some busted, like Pets.com was trying to reach a lot more people than other businesses could that didn't have access to a pet store, for instance, but that busted. But companies like Amazon were very successful. You go to a bookstore, this was like 20 years ago. How many people went to bookstores 20 years ago? Okay, so they're kind of cool places, but they had like 10,000 books, right? And people like, maybe there are 10,000 popular books, but Amazon could give you a million books offering. They had the big warehouse, and if there was a population of 100 people in the US who would buy a book, or maybe it was 1,000, they could carry that book. The local bookstore could not. So they found how to hit this heavy tail. Local bookstores kind of have been dying since then, right? There's still some out there, and those are the ones that are carrying things that even Amazon can't find, because they're like used books and stuff like that. Great. But so then going beyond this, Amazon in the dot-com era, they only went up so far in this distribution until like the Kindle and stuff. Now they can just store a digital copy and sell you that. It takes even cheaper to get further and further on this tail. And so you think of these as outliers. They're things that they're very far away from the popular part of the distribution. In this case for Amazon, it may look like this, like Tom Clancy novels and so forth, so many copies, right? But there's still 30% out here that was untapped, right? So what are the outliers in this data set, right? Some data sets, the tail just keeps going and you can't really chop it off anywhere. And so filtering out outliers or setting a parameter for what's noise and what's not noise is not the right way to approach it. You need to embrace everything going on here and build models or businesses that can hit this part of the distribution. Okay, I've run out of time. The zip distribution is about words. Let me just say, like the word "the" in the English language occurs like 7% of the time. The word of, so like "the" is like 7%. Of is the next most popular word. That's like 3.5%. and is like 2.8%. And if you look at the first dozen or so words, it follows exactly a zip distribution where this is 1, this is I equals 1, I equals 2, I equals 3, where C is 7%. The words in the popularity of words in the English language, this is pre-Twitter. Who knows, it's all hashtag stuff now. But they follow very nicely this zip distribution. It has a very heavy tail. There's lots of very rarely used words. Okay, cool. I'll stop there for today. So.